Okay, so now we're going to be talking about section 3.2, which, as I mentioned last time, is talking about different measures of, the book calls it dispersion. I've also seen it called spread. But it's basically how wide apart, how much does it, how far away does it go from center? So the first measure of that is really easy. It's called the range, and it's the maximum value minus the minimum value. Right? So whatever the maximum value of your data set is, you take it and you subtract the smallest value, and that's exactly how far apart your data is, right? But that can be useful, but it's only so useful because that can vary a lot depending on the type of data there is, right? If we're talking about SAT scores, right, those can sometimes differ by hundreds. But if we're talking about ages, or birth years rather, then maybe we're only gonna differ by, like, I don't know, 90 probably at maximum. And that doesn't say, like, if someone's range is 90 and another thing's range is 500, that doesn't say that they're all too much spread out. It means we have a different sort of measuring set for them. But it can be useful in some instances. But a far more frequently used one is variance. And this is one of those that has a different formula for sample or population. So sample variance, it has a different name, just like sample mean did. So it's the sum of, you take all of your data points, you subtract the mean from all of them, then you square it, then you divide it by the number of things in the sample minus 1. So n here means the same thing as it did last time. Little n means the number of things in the sample. The population variance, we again use the Greek letter sigma, right? So that's what this little guy is. It's the same up top, except of course we're using mu instead of x bar. But then down below, it's just capital N. So this is one where sample variance and population variance actually have a different formula, right? So you need to be even more clear here. Before, if you just wanted to find the mean, it didn't really matter whether it was a sample or a population, other than how you displayed it, right? Whether you used mu or x bar. But with variance, it actually changes how you calculate it, right? So your number's going to be wrong, not just your label, if you don't know whether you're dealing with a sample or a population. And the last one that we have, well, there's kind of two. One of them's not really a measure of spread, it's just something you use with these. But we have the standard deviation. And for both of these, it's just the square root of the one before. So s is equal to the square root of s squared, and sigma is equal to the square root of sigma squared. So if you want to find the standard deviation of a data set, first you find the variance of the data set, and then you take the square root. Right? So in a way, what this is doing, right, these two look a whole lot like the formula for mean, but instead of taking the average of the data, it's taking the average of the difference between the data and the center, right? How far away the data is from that middle point, right? The reason why we square it is that if we don't, it always winds up being 0. Because the positive and negatives are always going to cancel out when we add them together. So we square it to make it always positive, and then we take the square root at the very end to get rid of that square. So that what we're really trying to measure here in some way is, on average, how far is the data from the center. So that's what we have here. There's a couple of things that we can do with this. We can do the coefficient of variation, which is called CV. And for a sample, this is S divided by X bar times 100%. And for a population, this is sigma divided by mu times 100%. And the idea here is just to compare how big is the standard deviation relative to the mean. And it's often used to look for differences between two different data sets. And lastly, the thing we do with the standard deviation is, so we have some rules using the standard deviation. So if we're bell-shaped, right? So bell-shaped, it always turns out that the mean is this guy here in the center. And so this is the empirical rule. If this is one standard deviation out, actually I'm going to need to make it shorter. Alright, I'm going to have all sorts of bars here. So this is going to be one standard deviation out. This is going to be 2 standard deviations out. And this one's going to be 3 standard deviations out. Right. Then it turns out that we know that this is approximately 68% of the probability. This one, if we go out 2 standard deviations, is approximately 95%. And this one, if we go out 3 standard deviations, is approximately 99.7% of the data. So as we get bigger and bigger there, we have an idea of exactly how much is included. Now this only works for bell-shaped, and it's the better of the two approximations that were given here. Our second one is one of my favorite ones to say that I have to look up how to spell. Chebyshev's rule. It's true for bell-shaped, but it's not useful for bell-shaped, so we're going to go ahead and say this is a rule for not bell-shaped things. If something's bell-shaped, you should use the empirical rule. If something's not bell-shaped, then mu minus k standard deviations to mu plus k standard deviations has at least 1 minus 1 over k squared of the data. Right? So just as an example, what it says for so for 2 standard deviations, right? There is at least 1 minus 1 over 2 squared equals 1 minus 1/4 equals 3/4, which is 75% of the data in between these two numbers. Right, we notice this is still true for the bell-shaped, right? Bell-shaped says that there's about 95% of the data, and 95% of the data is bigger than 75%, so it's still true there, but the empirical rule tells us more, right? If we're not bell-shaped, then we don't know that we get all the way up to 95% like we do for bell-shaped stuff, but we do know that we're at least 75%, and that's better than nothing. So, those are our basic things. We mainly have variance and standard deviation. Range can sometimes be helpful, but it's also fairly simple. Mainly we're talking about variance and standard deviation here. And so we want to be able to calculate that, and we want to be able to play around with these estimations that we have right here. So let's do some problems. Let's see. Let's find sigma for the following data set. Let's see. 2, 4, 3, 5, 1. Right? So, if we recall, the formula is sigma equals the sum of xi minus mu squared all over n. So we need to know what n is. We need to know what mu is. Whoops. Then we're going to be able to find what sigma squared is, and then we're going to be able to find what sigma is, right? So there's a lot of hidden steps in this statement right here, right? Because the formula for sigma involves taking the square root of sigma squared. The formula for sigma squared involves knowing what mu is, and then the formula of mu we can figure out, right? So first off, n is 5. Mu was the sum of all the data divided by 5. So that's 15 divided by 5, which is 3. Right? And so now that I have this, I can plug into the formula for sigma squared. Right? So we're going to get 2 minus 3, because that's our first data point, minus mu squared, plus 4 minus 3 squared. It's our second data point, minus mu squared. Then we have our third data point, minus mu, and then squared, plus our fourth data point, minus mu squared. So our fifth data point, minus mu squared, all over 5. Alright, so that's negative 1 squared plus negative 1 squared plus 0 squared plus 2 squared. Whoops, this is positive 1. Plus negative 2 squared, all over 5. So we get 1 plus 1 plus 4 plus 4 over 5, which is 10 over 5, or 2. Right, so now that we found sigma squared, since we want to find sigma, we just need to take the square root of 2, and then we're done. So, that was, I don't know, that wasn't so bad. I happened to pick very nice numbers for it. So your usual data sets are not going to play quite so nicely. Plus, we only had 5 numbers. So that sounds pretty horrible, and I don't really want to do it. So, if I'm ever going to do something like this for realsies, I'm going to open up my calculator. I'm going to edit my list. My list 1. Oh, shoot. Was it 3, 4, 1, 2, 5? I don't know if it was exactly in that order, but those were the 5 data points. It doesn't really matter what order they come in. Then I'm going to go to stat. I'm going to calculate 1 variable stats. I don't want to put weights on it, so I don't need a frequency list, and I edited that first list there. And I can see that it found the average to be 3, right? That's something we found before. And then if we look here at this sigma x, I happen to know that 1.1421, so on and so forth, is square root of 2, right? If we didn't know what the answer was ahead of time, we would just have to approximate it, but usually that's going to be okay as long as we have enough decimals. So since we were finding sigma, we're all good, right? If we were trying to find the sample standard deviation, then what we would want is that capital SX that shows up right above the sigma, the one that reads 1.58113888301. That is what it gets when it calculates the sample, because remember the formulas are different, right? X bar and mu are the same thing as far as the calculator is concerned, because it uses the same formula to find them. But it distinguishes between sigma and S because it had to use a different formula to find each of those, right? So even if you want to find mu, finding X bar is okay. If you want to find sigma, though, you have to go with sigma x, whereas if you want to find S, you go with this capital SX that it has here above sigma x. So the calculator can find that way easier than we can. It doesn't really do the variance, though you can always just take that number and square it. You'll get some approximation errors, but it will do standard deviation for you here on the calculator. So going back to our whiteboard here, we're going to do another problem. So for a given data set, we have mu equals 1000 and sigma equals 75. Presume the data is bell-shaped. How much of the data is greater than 850? Right. So what that means is we've got a roughly bell-shaped curve here. We've got mu at 1000. We've got 850 somewhere over here. And we want to know what is all of this stuff. How much of the data is in that underlined place. Right? So if we think about back up here to the rule that this maybe reminds us of, we need to know how many standard deviations we are away, right? Because that's what our empirical rule tells us about, is being certain number of standard deviations away. So the way we do that is we figure out how far away we are in total, right, by subtracting two numbers from each other. That's how you figure out how far two numbers away are. So you subtract them. And if I want to know how many standard deviations that is, I'm going to divide that by the standard deviation we have. Right? So this is 2 standard deviations away. Right? Now, there we go. We'll go with this one. What's it called? The empirical rule that we have tells us that between this value and mu plus 2 sigma, so for this piece, we should get 95%. Right? But that leaves us a problem. That's not all we want to have. We also want to know about this piece. So there's a couple of different ways we can do that. The book goes through one way, and we'll do that first, right? And that is that the really nice thing about bell-shaped curves, let me get a different color here. The really nice thing about bell-shaped curves is that mu divides everything in half, right? So the fact that mu is dividing this mu minus 2 sigma and mu plus 2 sigma in half means that this piece is going to be 95 divided by 2%, which is 47.5%. Right? So just that green piece, since mu is exactly halfway between these two numbers, mu divides that chunk in half because it's the mean, not just because it's any old number, but because it's the mean and it's halfway between them, it divides that 95% in half. And because it's the mean, it divides the whole data set in half. So this part is 50%. Right? So that means that the part that we wanted, right, is this stuff is green plus orange. So we get 97.5%. Right, so that's the way the book does it, is it has you figure out stuff based on mu dividing things in half. But another way to look at it, and I'm going to draw a new graph with the same stuff. Alright, so we have this here, and we knew from before that, let me get the same colors, this stuff was 95%. So what that means is that everything else has to be 5%, right? Because that has to be everything, right? Something plus everything else has to give you everything. So that everything else has to be the 5% left over. And again, because mu is dividing this exactly in half, one of these is going to be that 5% divided by half, right? Only because mu is exactly halfway between them, right? So that means that the stuff that we care about in this case is blue plus green, which again is 97.5%. So there are a couple of different ways you can break it down using this, man, I always forget what it's called, empirical rule. Mostly keeping in mind the fact that when you are bell-shaped, specifically when you have bell-shaped data, mu separates things exactly equally, right? So if you have two pieces that are mirrored around mu, they're going to be exactly the same, right? If you're looking at everything to the right of mu, like was over here in orange, that's going to be 50%, right? Because mu divides everything in half. Right? So another sort of problem. So we're going to have a non-bell-shaped data set this time, where mu is 500, or x bar rather is 500, and s is 111. How much of the data set is between 56 and 944? Right, so again, like before, we need to figure out how far these are from x bar. So 944 minus 500 is 444. And we want to figure out specifically how many standard deviations that is. So that's 4. Hopefully, we're going to get 4 on this next one too. Right, when we figure out how far 56 is away. And it turns out we do, which is good. So if we have our data set, who knows, maybe it's a little wonky. We have 500 here somewhere. We have 56 and 944. And we have this is x bar and this is x bar minus 4s. And this is x bar plus 4s. And since we're dealing with non-bell-shaped data here, that means we have to look at Chebyshev's. Right? And Chebyshev's says precisely that when you're within, let's see, where do we have it written down? All the way up here. When you're within mu minus k sigma and mu plus k sigma, and this doesn't matter population or sample. But if you're in between those two, then you're going to have 1 minus k squared of the data. Right? So 4 is equal to k in this scenario because it's the number, right? This was x bar minus ks, x bar plus ks. So if 4 equals k, there's going to be 1 minus 1 over 4 squared of the data. That's 1 minus 1/16. That's 15/16. And when I threw that into a calculator, I got that was 93.75% of the data is going to be between those 2 points. Right? Because they are 4 standard deviations away from the mean. And so Chebyshev's says that we have that much of the data in between those 2 points. Right? So that is all of our measures of disbursement. Next, we're going to talk about, we're still going to call it measures of relative position, which is a weird sort of phrase. But largely next section is going to be all about how we can summarize a lot of the information about a data set. So that's what we'll be talking about next time.